The next example, I thought I recorded, but I just wrote there. Chapter 3 probability. So is it? I'm starting from well, starting from the first slide.
Yeah. Question 5.
Example 5. I've completed explaining example 5. Yeah. Confirm.
Yeah.
Okay. So yeah. This week we'll continue with that and try as much to cover as much as possible. Let me double check the form C first. Did you all had your breakfast?
Yeah.
I almost missed our class today because I really thought that our class starts at 9:30. And luckily I remember, oh no, Monday it's normally at 9 a.m. And luckily I managed to, be ready. I'm looking at Form B now, which today is week 4. Yeah, and I think I mentioned also last week that the chapter for probability, we have week 4 and week 5 to cover. Okay, so I was going through your coursework past few days now, and for your first test, which is on the, let me double check, on week 9, right? So there will be about 6 questions, okay? Well, short questions that will cover from chapter 1, 2, 3, and 4 for your first test, which is on week 9. Okay, still quite a far distance away. So that means our coverage for today will go for your test. Yeah. So for your test, there are 6 questions. Yeah, mainly from chapter 1 to chapter 4. And then you have your assignment, which is on week 11. That would be 7 questions altogether. And yeah, from chapter 2 to chapter 5. Yeah, for your assignment. I think I've briefed that to you guys. So let's start for your lecture notes for today. Are you all ready? Anything you would like to ask?
No.
Did I give you guys any work to do?
No.
Oh, none, is it? Oh, because we discussed it during the tutorial, right?
Yeah.
Yeah.
Okay, so let me start the recording and start our session. Okay, good morning, everyone. Today is week 4, and today's date is the 8th of February, 2021. Yeah, this is the week for Chinese New Year, which falls on a Friday. So luckily it doesn't falls on our class, or else we have to do replacement to it. So yeah, we shall continue with our lecture on chapter 3, And what we're going to do today, as what you see on the screen, is the laws of probability. So based on what we have learned last week, we have looked at the definition of probability and look at some examples. How do we calculate simple probability calculation? And what we're going to do today is basically look into laws of probability, and there are three main ones. It's categorized into three. What we have, first of all, is the complement rule. I've touched about it a bit during the lectures last week. And the addition rule and the multiplication rule. Now, it's just that even though here we identify the names of all the laws of probability, when we're doing the exam question or the assignment or the test, it's not stated like, okay, apply addition rule to this question, apply multiplication rule to this question. None. It's not stated. Yeah. So this is where I figure out that students are facing difficulty in deciding which one is the correct rule to use in order to answer the question correctly. So that is why it's very important that you should understand all these rules, and therefore you have a clear understanding of the question and apply the correct rule. Yeah. So let me start on the laws of probability. Like always, if you have any question, do not be shy to straight away turn on your microphone and ask me to clarify further on any topic. Or if you prefer, you want to write on the chat, also can, but it does take me a while to look into the chat page. So the first one is the complement rule. And what you see is simply probability of not A. I pronounce it as not A, indicating the complement of the set A. Meaning, when we want to find the complement rule, we want to find out what is the probability that is outside of A, or rather, what is not A. So that is why the complement rule is basically the total value of probability, which I've mentioned last week. Total value of probability is 1. And minimum value, the smallest value of probability, is 0. So in this case, in order to find the complement rule, we take the maximum value of probability, which is 1, minus with the probability of A. So that would allow us to get the complement rule. Yeah, because the question may be in such a way that instead of looking at the event to find out the probability of that event, the question might also ask to find out what is the probability of not that event. Okay, so I hope that is clear. The next one is the addition rule, and there are two types here. As you can see, one is what we classify as mutually exclusive events, and the other one is non-mutually exclusive events. Now, the difference between these two things is that mutually exclusive events are based on the experiment that there are two events, two or more events, perhaps, yeah? But if you look at the notation given here in green, it is only considering of two events, but it could be more, okay? So what addition rule states is that if we have the experiments such as mutually exclusive events, then you only have to add the probability of the first event A and the probability of the second event B. And the notation we use is probability of A or B. So the union here, this is the notation for union. We call it as OR, yeah? So an example of mutually exclusive events is like gender, like male and female. They are two totally mutually exclusive. And what does it mean by mutually exclusive? It means that there is nothing in common between the two events. Like what I mentioned, gender. You cannot have a person with both gender, right? You can either be a female or a male only. So this is how you solve or how you find the probability of A or B by just adding the two probabilities as given in the addition rule here for mutually exclusive events. Now, however, it exists non-mutually exclusive events. Yeah, as we know, everything is not totally independent of each other. There are cases where there are intersected area. So we call that as non-mutually exclusive events, which we have to apply this formula. It's the same as the mutually exclusive events. It's just that we have an additional value here. That means the non-mutually exclusive events, we have to subtract probability of A intersect with B. So you can see the formula, they are the same. But if your question is indicating it is non-mutually exclusive, then we have to add additional step here, which we need to minus probability of A intersect B. That means the area that is shared both by A and B, right? The multiplication rule, again, same thing like addition rule. There are two types. First is independent events, and secondly, dependent events. For independent events, it is quite straightforward. If I want to find probability of A and B, so notice that here is union, right? Here is intersection. Union is OR, but for multiplication rule, it's AND. That means I want to find out what is the probability of A and B. And here it is quite straightforward. You just have to multiply probability of A times with probability of B. So you see the difference. Addition rule, you add. Multiplication rule, you multiply. But we also have, if your experiment is dependent events, yeah, so we have to solve it. If let's say your example is dependent events, you have to solve it by probability of A times with probability of B given A has occurred. So perhaps maybe you need a bit of recalling back. What is this symbol that is looking like just a slash, backslash? Yeah, it's, we pronounce it as probability of B given A. Yeah, so for dependent events, we require this kind of step. So that means we multiply probability of A multiply with probability of B given A has happened. So the value of the probability definitely has been affected because A has occurred. Yeah, so all these laws, it's good if you can remember them. And of course, in order to remember them better, we have several examples as what you see in your notes in order to help you to remember all these rules accordingly. Yeah, so let's start with the example. So the first one is the addition rule. Let me just explain to you further about what does it mean by non-mutually exclusive events. Yeah. As you can see, it was stated here, right? Okay. So non-mutually exclusive events in addition rule, if probability of A or B, union always pronounced as or, then what we have is probability of A plus probability of B minus probability A and B. Yeah. Now the reason for this is because if you look at this diagram, Venn diagram, you can see probability of A enclosing all this area. probability of B enclosing all this area. And it has an area that is shared both by A and B. So that means this area, when you counted it for A, you already counted this area in the middle. And when you counted for B, you're also double counting the area in the middle. So in order to avoid from double counting, that's why we need to deduct the probability of A intersect with B, or probability of A and B. So that is what based on the formula given to you just now. Any questions so far?
No.
Okay, you understand, yeah? Farah, how is it? Okay, huh?
Yeah, okay.
How about you, Calvin? Are you all right? Do you understand so far?
Okay.
Okay. So in order to understand the example, as what you see here, in a group of 100 people, 40% owns a cat. So I've labeled the first circle here as a person who owns a cat, and 25 owns a dog. But it is stated in the question that 15 owns a cat and a dog. That means that 15 person owns both of the amount, owns both a cat and a dog. So there are 15 here. That is why we have to deduct the 40 people who owns a cat minus the 15 to indicate this area here. That gives us a balance of 25. And a dog, there are 25 people who owns a dog. That's why we need to minus 15. That gives us a 10. And as we know, there are 100 people in this group. So you have 15 plus 25 plus 10. That basically gives us a value of 50. And therefore, outside would be 50 as well. So that means in the group of 100 people, there are 50 people who doesn't own any pets at all. Okay, so the question is, find the probability that a person chosen at random will own a cat or a dog. So you see the key word here is or. So what happens here is basically probability of cat or dog, which we write it as probability of C union D, that correspond to or, as what you see here. And therefore, since when you look at the Venn diagram or even the explanation that is given to us, yeah, we know it is a non-mutually exclusive event. So therefore, we have to apply to the formula of probability of C plus probability of D minus probability of C intersect with D. So we know now that the value of C, yeah, total of C is 40 out of 100. Probability of D is 25 of 100 minus with 15 out of 100. Yeah, and when you calculate it, you should get 1/2 as your answer. So this is how you do it. Yeah. Now the next question is, owns a cat or a dog, but not both. Yeah. So that means we are practically talking about the ones inside here. Yeah, who owns a cat or who owns a dog, but not both of the animals. So that means probability of C or D, but not both, means we're only looking at probability of C plus probability of D, which means we only look at the value inside here, not inclusive the ones that is shared by both cat, the person own both cat and dog. So it's only 25 out of 100 plus with 10 out of 100, and that gives us 7/20. So yeah, if you have a question similar to this, the Venn diagram helps a lot in visualizing the question. Yeah, but some students, yeah, they can see it immediately how to solve it. They don't need a Venn diagram to solve it correctly. I hope I make myself clear on the explanation. Any question?
Do you write on decimal or fraction?
Oh, doesn't really matter. You can write it in decimal also, but preferably, well, a fraction. It doesn't really matter actually. Yeah. Now you ask me, Noel. It doesn't really matter. Yeah. Both answers will be accepted. If say a student write sorry, say if a student write in fraction, and let's say the marking scheme is in decimal, I would definitely convert the value just to check correct or not. So it doesn't really matter unless the question did specify on the question that you must write to a certain method. Yeah. Okay. All right. So moving on to example 7. Before I move on to example 7, you can see that from the question, even though the data given to us is a non-mutually exclusive events, you can see the way the question was asked in part B, that it was referring on mutually exclusive events only. Yeah, for part B. So part A was more on non-mutually exclusive concept, but part B is more on mutually exclusive concept. Yeah. So we go on to example 7. In this case, we have 20 adults, 4 out of the 7 women. Yeah, 4 out of the 7 women and 2 out of the 13 men wear glasses. So there are 7 women and 13 men from the 20 adults. Yeah. And this is about a person is wearing glasses or not. Yeah. So here we know that the probability of women is 7/20. Yeah. So because there are 7 women. And also there are 13. Oh, from the information that we get from the question, we have 4 plus 2, that gives us 6 out of 20 are wearing glasses. Now, what the question is asking is, what is the probability that a person chosen from the group is a woman? That means we want probability of a woman or someone who wear glasses. So that's why our focus here is a woman, probability of W, and probability of wearing glasses, 6/20, because this is definitely a non-mutually exclusive events, because we have cases a woman and wearing glasses, and we know there are 4 of them. Yeah, stated here, from the 7 women, 4 are wearing glasses. So we can conclude 4 out of 20 that satisfy these 2 conditions: woman and wearing glasses. So therefore, in order to solve this question, the probability of women or wear glasses is equivalent to probability of W union G, woman and wear glasses, and therefore probability of W plus probability of G minus probability of W and G. Yeah, woman and glasses lah. So since we already stated all the values accordingly, just put all the values and calculate it. 7/20 plus 6/20 minus 4/20, that would give you 9/20 as your answer. Okay, any question?
No.
Okay, moving on. Now this is a slightly different question. There's not so much, but there is several conditions stated here. We have 1 white die and 1 black die are rolled. And first question is that we need to find the probability the white dice shows 1 or 2, or the sum of the dice is greater than 9. So notice here, the keyword is or. Yeah, so we have 2 conditions here. So in order to answer this, yeah, I hope you understand the scenario. You know, a dice has 6 numbers on it, isn't it? Number 1, 2, 3, 4, 5, and 6. But the thing is, we have two dice. One is black and one is white. Yeah. And we want to find the white die shows 1 or 2, or when you add the two dice, it must be greater than 9. So that means when the dice, you have one black and one white, when you add the dice, it must be greater than 9. That means you should have 5, 5 or 5, 6, because only that combo will give you a value. When you sum it up, it is greater than 9. Therefore, first of all, we need to consider what is the sample space S. So these are basically, you have to list out all the numbers, not numbers, all the combo of the dice, the probable combo of the dice. That means we have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, then 2, 1, 2, 2, 2, 3, until you list it out to 6, 6. Of course, I'm not going to list it out all here. I just write it in this manner. So therefore, there are many combinations here. Yeah. So from here, we know the number of the sample space are 36 because you have 6 rows, 6 columns to represent the sample space. So that's why we have 36 number for the sample space. Now, in order to answer the first part, the condition stated here, I label it as A, is that the white dice shows number 1 or number 2. So that means, yeah, that means for A, the elements are, you can see, assuming that the first dice here is the white one. Yeah. So you see 1, 1, 1, 1, 1, and 1. And here as well, the first dice, white, is 2, 2, all the ones that shows a 2. So basically, these are the ones that satisfying the first statement here. The white dice shows a 1 or a 2. And here we have 12. For the number that is satisfying A, there are 12 numbers. All right. Now, when we write it in the form of probability, we have probability of A 12 over 36, which is 1 over 3. So that settles concerning with the white dice. Now, moving on, I hope that is clear, yeah? So far, so good, class. Are you following me okay?
Yeah.
Yeah.
Okay, no
Yeah.
problem, yeah? So moving on, we also have to consider the rest, yeah? The sum of the dice is greater, sum of the dices is greater than 9, which is basically the sum must be 10, 11, and 12. So if you consider that for B, where the sum of the dices is greater than 9, we have 6, 6, 6, 5, 6, 4, 5, 5, 4, 6, and 5, 6. Now remember here that 4, 6, and 6, 4, even though they look the same, but they are not. Because remember, the first dice is the white one, the second dice is the black one. Yeah? So we have 1, 2, 3, 4, 5, 6 here. Our N is, for B is 6. Therefore, probability of B is given here as 6 over 36, which is 1 over 6. So based on what we have for A just now, we can actually get calculate it already. But we have a C. Let me go back to the question, whereby it's stated here, for B, the white dice show 1 or 2, but we also have another scenario, both dice shows the same number. So if you consider that we only have these 6 numbers, 6 combination that the dice have the same number. So that means 1, 1, 2, 2, 2, 3, 4, 4, 5, 5, and 6, 6. Again, there are 6 numbers here. Yeah, so 6 over 36 gives us 1 over 6. So from here, we know that A intersect with B gives us a null set. Because if you compare the A just now, look at the A. Yeah, these are the elements of A. Yeah, we have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and so forth. And looking at the B, the elements for B, we know that there is no similar combination between A and B. So we can declare probability of A intersect with B equals to 0. Okay, class, so far? So here, in order to answer probability of A union B, remember A is the dice, let me go back. A white dice shows a 1 or a 2. Yeah. Yeah, A is a white dice showing a 1 or a 2. We know the value for probability of A already. And also, probability of B is the sum of dice is greater than 9. We know it is 1/6. And we also, based on the statement stated here, that A intersect B is null, 0. There is no similar element of the combo between A and B. So that's why it's a 0. So you just have to put the value of A, probability of A, which was calculated earlier. We got 1/3. And probability of B is 1/6 minus 0. And that would give us the answer as 1/2. Any question, class? Okay. No question, is it?
Why do I have to minus? Just because it's a non-mutually exclusive.
Yes, it is non-mutually exclusive. That's why we have to minus. Because all these dices, the condition given, it indicates to us that it is non-mutually exclusive. But it so happened that because of the question, the word or in the question, and we are using union, and therefore applying the formula anyhow, the value is 0, right? So it doesn't really affect your answer. Even though if you use the mutually exclusive events, you still get the same answer. Yeah, but I just want to show clearly that because there is no intersection between them, yeah, so it's 0 lah. So that's why it's 0 here. Okay. Then we have the next one, A intersects C, because if you compare the elements of A and the elements of C, two numbers or two combination are the same between A and C, which is 1, 1 and 2, 2. It exists in the set of A, it exists in the set of C also. So that means probability of A intersects C, there are two numbers. Yeah, two combination. So 2/36, we get 1/18. So in order to answer the question of probability A, from the white dice appear 1 or 2, and C is the dice shows the same number. So probability of A plus probability of C minus probability of A intersects C would be 1/3 plus 1/6 minus 1/18. And that would give us 4/9 as the answer. Do double check the value, yeah? I believe the answer is correct, but I hope you have a calculator with you and you can double check the answer that I shared as well. Any question for this question? Yeah?
No.
No, huh? Everyone is clear. Okay. Moving forward. Okay, so just now was non-mutually exclusive events. This time, addition rule, mutually exclusive events. Yeah, this is events that cannot happen at the same time. That means it does not overlap. Yeah, the event doesn't happen at the same time. That means the probability of one event will not affect the probability of the second event. There is no intersection between them. So this is the formula we're using. Probability of A union B equals to probability of A plus probability of B, of which you can visualize it on a Venn diagram. You can see the set A and the set B. There's no intersection whatsoever. It is on its own. So the probability of A intersect B is 0. There is no chances that there are intersected. So that's why we have it's equal to 0. So this is an example. Say you have a dice, it is only thrown one time. E is the event of getting an even number, and O is the event of getting odd numbers. So you see, when you have a dice and say the event of getting an even number, it has no effect on the event that gets an odd number, because the even number and odd number doesn't mix. Yes or not? However, the question here is, are the two events mutually exclusive? You can see the answer already. It is mutually exclusive, because by logic, you know it is mutually exclusive. But how do you prove it? So in this case, what you need to do is to list out E is for even, right? 2, 4, 6, and odd is 1, 3, 6 on one dice that you throw, right? So this proves that E intersect with O, even intersect with odd, is a null set. We call this as a null set, empty set. It doesn't exist, and therefore we can say probability of E intersect O is equal to 0. Yeah, notice I've written probability here. It's equal to 0. Hence, we can say E and O, the event E and event O, E for even, O for odd, they are considered mutually exclusive. Yeah. Yeah. This is how you answer example 9. Any question?
No.
Mhm. Okay. Moving on. Next is independent events and dependent events. I've explained basically about it also just now, but just to mention about it some more, my battery is running out, so let me plug that in first. Now, independent events, I've explained just now, right? So I'm mentioning it again. Two events are said to be independent if the occurrence of one event A does not affect the occurrence of event B. And of course, vice versa. Yeah. So this is given to us like this. The probability of A given B is equal to probability of A, or probability of B given A has happened is equal to probability of B, or probability of A and B is equal to probability of A times with probability of B, multiply. Yeah? So this one has been informed to you, but not these two. So that means when we say, or our experiment given to us, they are not not affecting each other, and therefore it is independent. Hence, if I want to find the probability of A given B has happened, it's still equal to probability of A, because it does not affect to A. Whatever happened to B, it does not affect the probability of A. So same thing vice versa, as you see here. So independent events is such that the occurrence of event A will not affect your occurrence of event B. They are totally independent. Yeah. However, for dependent events, yeah, two events A and B are said to be dependent if the occurrence of event A affect the occurrence of event B, and vice versa. So do take note, the probability of A, yeah, probability of A given B has happened is not equal to probability of A any longer. because it will affect the value of A. The value of A, the probability of the value of A would change after the effect of what happened in B. So same thing, vice versa. And here, probability of A and B is not equal to the multiplication of probability of A and probability of B. Yeah. So does that make sense? I hope it does. And perhaps by showing an example, yeah, I hope you guys will understand this better. Yeah. So we have example 10. This is talking about a dice. It's thrown twice. So you can visualize it. 2 dice are thrown. And A is the event where 3 is obtained on the first throw, and B is the event where an odd number on the second throw. Now remember here, this is not talking about 2 dice. Yeah, this is talking about 1 die, but it's thrown twice. That means it's the same dice thrown. Yeah. And there are 2 conditions set there. We have event A, 3 is obtained, and B, odd number is obtained on the second throw. Are the 2 events A and B independent or dependent? So if you think about it, probability of A is a 3 is obtained, and as you can recall, a dice, you have 6 numbers on the dice. The number 3 is obtained on the first throw. That's the event for A. There's only one number 3, so the chances or the probability of it is 1/6. Yeah. So if we consider the event B, whereby it's the same dice and it's thrown the second time, and the event is odd number on the second throw, we have 3/6, because on the dice there are 3 numbers. The number 1, number 3, and number 5 are the odd numbers. Yeah, so 1, 2, 3, that's why it's 3/6. And therefore, simplified, you get 1/2. Now you see here, class, the event A and B. Yeah, event A and B is such that you see the number 3 satisfy A, and B are the odd. So that's why you see 1, 3, and 5. So the intersection between them, A and B, are these 3 combo. 3, 1. Yeah, the first value here, 3, is satisfying event A, and B, whereby the odd numbers are the 1, 3, and 5. Yeah, so from here, that tells us probability of A and B, there are 3/36. Yeah, 3 numbers out of the total number, which are 36. That gives us 1/12. Because remember here, the question is asking, are the 2 events A and B, is it independent or dependent? So therefore, you just multiply probability of A times the probability of B. That means 1/6 times it 1/2, as you can see here, gives us 1/12. So you see here, class, the similarity between them. Probability of A and B, which is 1/12, and probability of A times probability of B is also 1/12. So event A and event B are independent, because when you multiply this, it's equal. I mean, when you show this, probability of A times probability of B, it is equal to probability of A and B. And this is the answer. Any question? No, dear.
No.
Okay. Farah, okay?
Yeah.
How about you, Calvin?
Yeah.
All right. So we move on to the next example. Now, the next example is, say, a student students take 2 independent tests. It's not one student, but the students took 2 independent tests, 2 tests. 30% of the students pass test A and 60% pass test B. Yeah. So 2 independent tests. Of course, now we already know it's an independent event, right? So if 30% of the student pass test A and 60% pass test B, what is the probability? Find the probability of both tests, only test A or only one test. So for this, we have to list out all the information here, like 30% for test A. So what I have is probability of A is 0.3. Therefore, it will be 0.7 who did not pass. Probability of B is 0.6, then 0.4 did not pass test B. So if I want to find out probability that the student passed both tests, therefore probability of A and B is such that, because both tests are, so that's why we want to find probability of A and B, is that we just have to multiply probability of A times probability of B. Yeah, so that gives us 0.3 times 0.6, and the answer is 0.18. Okay. Right? So if only test A, that means it's this probability of A and not B. Yeah. So same thing, and we multiply. Yeah. Probability of A multiply with probability of not B, and therefore we have 0.3 times 0.4. And only one test. You see, in this particular question, is that it doesn't specify which test. Is it A or is it B? So in this case, we have to consider all probability that it could be A pass, B do not, or it could be, or you see it's plus, A fail and B pass. So if it didn't specify the, what do you call it? It didn't specify which, which specific test that is pass or fail, then we have to do it this way. Yeah, that means we have to consider all possibilities, of which when you multiply, you should get this answer. Okay, any questions so far, class?
For the
Mhm.
the one, the 0.3 times 0.4 on question C.
This one.
Oh yeah. Can we replace with 0.12 directly?
Oh, because you already obtained the answer earlier, yeah? Of course you can.
Oh, okay.
Yeah, because you already shown the working earlier, so it is okay. All right, so let's move on. Would you like to have a break already? It's already 9:51. I think it's quite a lot already, can we have a break?
Okay.
Okay.
Yeah, about 15 minutes, because I'm starting a new one. It's called conditional probability. So it's a good time to have a break. All right, see you in a bit, like maybe 10:05, like that. Okay?
Okay.
You
Okay.
guys. welcome back everyone. Hello? Is it all
yeah.
of you over here? Yeah. So that was a good short break. And we're going to continue. Yeah. So the next one is the conditional probability. This one is using this notation. If you look at this notation, it's some sort of like a backslash, and I normally pronounce it as given that. Yeah, that means I want to find the probability of A. However, to find probability of A, given that event B has happened. Yeah, that means event B has occurred. Event B has occurred, therefore it has an effect on the value of A. So the notation we use is probability of A given B, and then, however, in this case, when we want to calculate the conditional probability, it must be that the probability of B must never be equal to 0, because if it's equal to 0, it doesn't allow us to get the answer. So the probability of B should not be equal to 0. Then probability of A given B has happened is equal to probability of A and B divided by probability of B. Now this is the formula of the conditional probability. Yeah, and it has been proven as a conditional probability formula. We are not required to prove this formula. Yeah, however, just to help us to remember this formula better, you see, if you want to find probability of A and probability of A given B, then the denominator would be the intersection between the two sets or the two events A and B, in such that that's what you write on the denominator part. Numerator part, probability of A and B, and the denominator part is probability of B following what is the given value. So this is how I always recall this formula, that in
One
order.
deck.
Oh, sorry.
Okay. I found this on the web for numerator probability of A and B and the denominator.
Sorry, that was my Siri interfering our session. As I was saying, to find probability of A given B is, of course, to find probability of A and B, the intersection between A and B, and then you divide by probability of B, which is the given value. So every time when you want to find conditional probability for two events, the probability of A given B, the top part, the numerator part, is where you find the intersection between them, and the denominator is probability of B, the given value. Yeah, so when do you use conditional probability? Normally you use conditional probability whenever there is a question. On the question, it stated the word given. Therefore, when the word given is stated in the question, you know it's a conditional probability, because the word given is indicating to us that to find a probability given that something has happened. Yeah. Another term that is always used is the word if then. That's why I purposely have it here, if then. Yeah. When you see in the question the word if, a statement, then a statement, that is also an indicator that that question you have to solve using conditional probability. But of course, we're going to look at a few examples so that you'll be familiarized with the method. Just to highlight to everyone, conditional probability is important, especially in your tests. Yeah? Because your tests, inclusive of chapter 4, even your assignment, yes, you have questions on chapter 3 also. Yeah, probability, especially conditional probability. So if we swap the position, yeah, if we swap the position, just now was A given B, now probability of B given A. Notice that now it's B intersect A on the numerator part, and the denominator is in accordance with the given value, probability of A. Yeah, so that means it is okay to write it as probability of B given A because of commutative law. It can be written as probability of A and B. It's the same, divide by probability of A. Yeah, so from here, oops, too fast. Yeah, just to make it aware to everyone that probability of B given A is the same as you write probability of B and A and probability of A and B because of commutative law. So it's okay to write it in this manner because the denominator is still the same. Yeah. So let's look at example 12. How is it applicable? So this is a simple example. When one dice is thrown, say odd number is obtained. What is the probability that the number is a prime number? So this is a simple example. So you see, I let O as equivalent to odd number is obtained. That means O odd number, we have 1, 3, 5. So that means probability of odd number is 3/6 because we know when you throw a dice, the sample space are 6 numbers. So 3s, as you count here, over 6. So probability of odd is 3/6. Okay, which can be simplified to become 1/2. Now the next condition given to us is probability of P, where P is the prime number is obtained from, i.e. probability of prime number is 2, 3, and 5 from the 6 numbers. Yeah, the number 2, 3, and 5 are the prime numbers. And of course, probability of P is 3/6 because there are 3 numbers from the 6 numbers from the sample space. Again, simplify it, you get 1/2. So therefore, the probability of odd and prime, yeah, is given as odd and prime. There's only 2 numbers. They are odd, 3 and 5, and they are prime numbers. And this is basically 2/6, simplified to become 1/3. Yeah? And hence, if I want to find out the probability of prime number, given that it is odd number, you can see I'm using the backslash symbol to indicate, because first of all, the condition that the number is odd, yeah, that's the given condition. And what we want to find out is what is the probability that the number is prime number. So that's why we are looking for probability of prime given it is odd. So that's why it's written in this manner. And just like the formula that I've explained to you just now, it is probability of P intersect odd, prime intersect odd. You can see the intersection between these 2 numbers. And then divide by probability of odd based on the given value. So we already calculated all this, which is prime and odd is the same as odd and prime. And we got 1/3 for it, as you can see here. And probability of odd here is 1/2. So when you solve this, you get 2/3. And therefore, that is our answer. Oops, too fast. Yeah? Any question?
So that means there are 2 layers, like 2 probability.
2 probability. What do you mean by 2 probability, Noel?
Like first have to find the probability of odd number,
Yes.
and then
Yes.
oh,
Yes, that's, I mean, you have to find out. Well, basically, need to understand that the question is we want to find the probability of prime numbers given it is odd number. Yeah, because if you read the sentence, it's stated that the dice, first we get odd number, it's obtained. Then we want to find out what is the chances that it's prime number. It's the same number, but we just want to find out what is the probability that first the given condition is it must be odd, and then we want to find what is the chances that it is prime. So all this working here is basically just to assist in the final solution, because once you identify what the question wants, which is the probability of prime numbers given that it is odd, we apply the conditional probability formula, just what as you see here. Remember I said the numerator, just find the intersection between these two values, these two events, and the denominator follows what is the given. So once you have identified the conditional probability, that's why it's important to find probability of prime and odd, which we obtain from here, divide by probability of odd, which we have listed earlier. So some students, what they do, yeah, they simply immediately work on the formula and then they start looking for the answer. But what I explained here is I explain how to get the answer first, the values for each of them, before I put it into the formula. Yeah, so I hope that is clear and understood. Okay.
okay.
Right. I also have example 13, and you notice or not, this question in example 12, the word given and the word if then is not in the question. It's just that when you read the question, it's implied that odd is the given one and prime number is the one we want to find out. So sometimes question like this, student miss out that the question is requiring you to do conditional probability. So that is why need to read the question carefully, especially statistic paper. Statistic paper, there's a lot of words on it, not like discrete mathematical structure that you did the first semester. Remember, it's very structured kind of question. It's very just numbers and structure, isn't it? But here it's like an essay. You have to read the question and understand what the scenario is. So some students, they like statistics because they prefer the reading part. But some students, they find it's too difficult to understand the storyline behind the question because there's a lot of words. Yeah. So what I'm saying is, if you look at example 12, the word given or the idea of if then, as what I explained to you earlier, is not even in the question, but it is a question requiring you to use conditional probability. So if you compare with the example 13 that we're going to do next, you notice that I've highlighted the word given. This is an indication that we would have to solve this question using conditional probability. So we have a probability that the student will fail accounting, 0.2, mathematics 0.15, and fail both 0.03, probability of A and M. What is the probability that he will fail accounting given that he failed mathematics? So if you look at this question, what is the probability that we want to find? Probability of what is given? Given is he failed mathematics. So what is the probability that we want to find? Is that he failed accounting. So that's why you see here probability of A given M. That means the given is he failed mathematics. And what we want to find is probability of A. So can you try it out before we check? Before we discuss the answer? What is your final answer?
Is it 1/5?
I can't remember the answer. Let me see. So that means you have to find out probability of A and M, which is 0.03, and probability of M, which is 0.15. So divide them, you get, yes, correct, Kelvin, it is 1/5. Because 0.2 is 1/5, yeah? So that's how you do it. It's as simple as that. But of course, in exam, your question won't be as short as this. Your question would be a process of drawing the tree diagram first, and then from that tree diagram, you have to derive the solution. Like something like this, like asking a given question. So there would be two parts there. You have to draw the probability tree, and from the probability tree, you apply the conditional probability formula to find what the question is asking. Okay, so did you understand, Noel and Farah? Because did you get the same answer? Because Calvin already stated the correct answer.
Hi.
Yeah.
Okay, good. Right. So I hope the conditional probability concept you understand. It's very simple. Perhaps in your notes it's more detailed explanation, but I shortcut it. Perhaps I don't really remember the last time I looked at your notes, quite a while ago, because I prepared my slides earlier. But I hope you understand the concept of conditional probability. And of course, on the net, on the internet, yeah, you can Google, go check on YouTube. There's so many explanation about conditional probability. You just type conditional probability, and the explanation on the internet is a lot more, yeah, explanation. But what I have shared with you concerning with conditional probability are the knowledge that you must be aware of, the basic thing about conditional probability, and what you need to know in order to be aware to how to answer the exam question, especially. And that includes your notes, your tutorial, yes, and also your assessment, that is your coursework, your tests, and your assignment, which I believe you all know now how important it is to score well in your coursework. Because when you score well in your coursework, yeah, it helps you so much in your final exam, because as you know, your final exam, you must get 40 marks and above. If you get below 40 marks, it's an automatic fail, yeah, even though if your coursework mark, if you add the final marks, you get a pass. But if you get below 40 marks in the final exam, it's an automatic fail. Yeah, that's the regulation at TAR-UC. That's why those who pass or graduated from TAR-UC, you know, they have made an effort to pass the paper. Yeah, because I believe some other colleges, yeah, if your final exam you get 10 marks only, but because your coursework you did very, very well, you'll still get a pass, but not at TAR-UC. That's, yeah, I believe that is so. Well, moving on to the multiplication rule, yeah, say A and B are two events defined in a sample space. And if A and B are independent, then you just have to multiply the event A and event B. And the notation we use is simply the intersection. Yeah, A and B. We pronounce it and or intersection in sets. Yeah. However, in dependent events, the probability of A and B, notice here, we can find the probability of A and B is equal to probability of A times probability of B given A has happened because they are dependent. So the probability of B is affected by what happens in A. So same thing, if we do it the other way around, probability of B times with probability of A, we have to consider what happened in B. Yeah. So independent events, we have to apply the conditional probability. But for this case, yeah, when we look at a probability 3, or even when we list out the values of the given value, we do not need to apply the conditional probability formula. We just have to look at the data or the experiment that was given to us to derive what is the value of the given value. Yeah, I'll show you in an example in a short while. Yeah, so this is example 14. Say you want to take out 2 cards from a shuffled deck, and we want to find out what is the probability that the first card is an ace and the second card is a king. Now we assume that the first card is not replaced before the second card is drawn. So this is the keyword actually, class. The keyword here is the first card is not replaced before the second card is drawn. Not replaced. That means the amount of cards in that deck of cards, in a card, there are 52 cards, right? So one of them, if it's being taken, it is not replaced. So here, probability of G1, that means this is the first card. Yeah, first card is an ace, and G2 is the second card, is a king, assuming first card is not replaced. So I hope you can visualize this. Yeah, in a pack of cards you have 52 cards. Yeah, and in the 52 cards you have the hearts, the spade, the club, and the diamond. Yes or not? And each of the shapes that I mentioned just now, there are 13 each. So 13 times 4 is 52. Yeah. So that means, since this question, I want to find out the probability of first card is an ace, we need to find out, and the second card is a king, as stated here. We want to find out what is the probability of getting the first card is an ace and the second card is a king, assuming the card is not replaced. So this, when we want to find out the first card, which is an ace, how many ace A in the pack of 52 cards? How many are ace? Do you know your cards well?
No.
4.
Yeah, there are 4 A's, isn't it? So that means you need to find out 4 over 52. That is answering the probability of G1. That means the first card is an ace. There are 4 A's, the A in the pack of cards, so 4 over 52. Now, when you want to take out the second card, remember here, probability of G2, second card is a king, assuming that the first card is not replaced. When you have taken one card out, because even though it's written here as 4 over 52, we only assume only one card is taken out. So how many left in that cards is only 51 cards. And because we want a king, it will be how many kings? there are only 4 kings as well. So that would be 4/51. So this is an example showing us dependent events. Yeah, because the second event, probability of G2, which is the second card is a king, it is depending on what happened in the first event, which is the G2. Yeah, so that's why we have 4/52, 4 aces out of the total 52 cards. But since the cards are not replaced, so that's why it's reduced to 51 now. But the king is still 4 cards. So that's why it's 4/51. So when you multiply them, that would give you 16/2652 as the answer.
If the first card take out is a king.
Okay. You mean the first card is a king? Then the
Yeah.
second card is also a king. Yeah?
Yeah.
Okay. If the question is, if the first card is a king, then the second card is also a king, assuming the first card is not replaced, then we would have 4/52 times 3/51. Because the first king already taken out, so there's only 3 king left. So 4/52 times 3/51.
Okay.
Okay, so that is how we answer the question. Is that clear, everyone?
Yeah.
Okay, good. All right. Okay, this one is a bit long, yeah, this example. And require a bit of thinking at least. Yeah, because you see, we have the word at least, 2 games will end in a tie. So you really have to understand the scenario. Okay, we have 2 persons here, Sui Ling and Chi Sang. They played 10 games of chess. 10 games of chess, okay? And 6 of them are won by Sui Ling, and 3 are won by Chi Sang, and 1 game ended in a tie. That means nobody win, nobody lose. It's a tie. So 10 games altogether. Now they agree to play another 3 games. Yeah, they want to play another 3 games. So basically, the information about winning 6 games and winning 3 games and 1 in a tie are actually helping us to get the probability values. Yeah, and now they want to play another 3 games. So in total, there are 13 games altogether. Yeah. So the question is, find the probability that Sui Ling and Chi Sang win alternatively for the 3 games, and Chi Sang wins at least 1 game, and 2 games will end in a tie. So in order for us to solve this question, we have to, put some information down first. So we have probability of A, which is Sui Ling wins 6 out of 10, which is 0.6. Then probability of B, Chi Sang wins 3/10, which is 0.3. And we have another one, which is C, probability of C, Sui Ling and Chi Sang, it's a tie, which is 1/10, 0.1. So it would be good to list it all out first like this, so that it's more organized. Could you hang on a bit? Yeah, I need to get my back hurts, so let me get a pillow for a while. Yeah. It's only Monday and I'm already getting my back painful. I couldn't sit too long. I must, move about. Then I feel better. Well, anyhow, let's continue. I got my pillow back. I got my pillow at my back. So the first question is, because we already list out all the probability values, right? So the first question is asking, Swee Ling and Chi Sang win alternatively. So if you consider this, there are 3 games. It can only be 2 cases. Swee Ling win, Chi Sang win, Swee Ling wins. Or it could be Chi Sang wins, Swee Ling wins, and Chi Sang wins again, because it says alternatively. So these are the possibility of the winners. Yeah, it could be, well, S is Swee Ling, Chi Sang, Swee Ling, or Chi Sang, Swee Ling, Chi Sang. So this is where you have 0.6 for Swee Ling and 0.3 for Chi Sang. So you just multiply all this and add them up to give us 0.162. Okay, so that's how we solve for the first part. The second part, Chi Sang wins at least 1 game. So this one you have to be extra careful, especially when the question is talking about at least. Oh dear. Can you all hear me?
Okay.
My mouse is not moving now. I wonder why. Hang on. Mhm. You can see my mouse there, right? Like the arrow. I'm moving my mouse. Now it's responding. Okay, better now. Doesn't move just now. Okay, so if Chi Sang wins at least 1 game, so what we do, because the only case that, there's no game that Chi Sang wins, is that all 3 games Chi Sang did not win. Because here we want to find out Chi Sang wins at least 1 game. So as long as Chi Sang win 1 game, or 2 games, or 3 games, are all considered as the answer. So rather than listing out all possibilities, there would be 8 of them. Yeah, Chi Sang wins at least 1 game. 7 actually. The best way to solve it is using the complement method, using the value 1, which is the total value of probability, and minus with the probability of Chi Sang wins no game. So when you do that, you only need to have 1 minus 0.7 times 0.7 times 0.7, and that would give us 0.657. So this is where we use the complement rule to solve the question. Rather than you count 1 by 1 until there's 7 scenarios of Chi Sang wins at least 1 game, it's best to use 1 deduct the probability of Chi Sang wins no game. That means 0.7 times 0.7 times 0.7, and that would give us 0.657. And I hope that is clear, yeah? And the third one, 2 games will end in a tie. It means that the 2 games, they win in a tie, and 1 game do not, because the condition is only stated 2 games will end in a tie. So here T indicates that it's a tie. T with a hat indicates it's not a tie. So from here, to win the games as a tie is 0.1 times 0.1, and not a tie is 0.9. And we times 3 to it, because all 3, they are the same. You see here is 0.9 times 0.1 times 0.1. Then plus 0.1 times 0.9 times 0.1. And here is 0.1 times 0.1 times 0.9. So all this, when you multiply by 3, you shall get 0.027 as your answer. Any question?
For question 2, if let's say wins at least 2 games, how?
Oh, if at least 2 games, yeah, that means you can, because it could be equal number then, that means you have probability of, he wins, she sang is a he or she, I don't know. So C, not C. Sorry, I'm in right. Same case lah. Like Chi Sang wins at least two games. So that means Chi Sang could be in the middle, yeah? And then, because there would be 4 scenarios, yeah? Wins 2 games. And another one is the CCC.
Oh, okay.
Because it says at least one, you said at least 2 games, right? So if it's 2 games, then you have to list it all out like that. But if it's at least 1 game, then it's better to use this method. If it's 2 games, there is no easy way. You have to list all 4 lah. But of course, this one you can simplify by just multiplying by 3. Yeah? Times 3 of the one of them. And then you plus with all games are won by Chi Sang.
Okay.
Clear now? I hope so. Yeah, everybody is clear. Okay, moving forward. Next question. Oh, probability tree now is in corresponding to the example 16. Yeah. Can I go back a bit and check how many slides I have left? If not, we are too far ahead. Oh, still a lot. Yeah, I have until slides number 64. Now we are at slide 27. Just do a bit more because we still have time, right? So after we're done, then we can start looking at what tutorial question to prepare for tomorrow. Yeah. Yeah. Let's do this. Are you all okay?
Okay.
Still can take some more.
Yeah. Okay.
Okay, good. Okay, looking at the probability tree, this is a very useful way. I sometimes, in order to help me to visualize the probability question, I use the probability tree to help me understand the scenario. And what is important is that you should presented all the outcomes as branches of the tree. So this is talking about a coin, which the coin is thrown twice. Yeah. So the first row is where you see here, we have head and tail. This is the first row. And then carry on to the second row, which the probability of you getting a head again, that means you have head and head. First row head, second row head also, or it could be head tail, or first one you get tail head and tail tail. So this is just a simple presentation of 2 coins. And if you have 3 coins, not 3 coins, basically, the coin thrown the third time, these are the outcome. So basically, you have sample space, head, 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 tail, head, tail, head, head, tail, tail, and until tail, 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 and all listed here. Yeah. So in your assessment, either in the final exam or in your coursework, questions will not go until 4 coins. It's only up to 3 coins, as you can see here. This is the first, second, third coin thrown. Yeah. In exam or in your assessment, coursework, questions will not go overboard until 4 times. Yeah, the coin is thrown, because that can get very complicated, and that is why cases like that, we need the computer to do that for us. Yeah. For manual calculation for the purpose of exam, I've seen question up to 3 coins, as what you see on the screen. Yeah. So based on the probability tree, of course, if you can recall back to your studies during your high school or in your foundation, labeling the branches as what you see here, head and tail, referring to the coin, head and tail. It is also important to label the branches, what value of probability it is. And when we're talking about head and tail, they are equal, right? Like the head is 0.5 and the tail is also 0.5. Yeah. And for this kind of example, of course, when we say about throwing a coin, it has no changes when you throw the second time. That means here is 0.5. Going to the second throw would also still be the same value, 0.5. Yeah, same thing with the tail, right? So here I have a slightly different idea though. We have 20 cassettes, of which 4 are defective. Defective means broken. And we want to take 2 cassettes. Yeah. And it's with replacement. So I've highlighted the word with replacement in such that once you have taken 1 cassette, yeah, it's replaced. So the number still maintain 20 cassettes. There's no reduction. Yeah. This question basically wants to find out what is the probability that both are defective. So labeling it, probability of D1, first cassette selected, and D2, second cassette selected. So here, what I want to find out is probability of the first cassette and the second cassette, because stated here in the question, I want 2 cassettes. Yeah, probability of D1 and D2. So in order to visualize this, yeah, we're going to draw a probability tree. And based on what we have covered so far, this is representing a multiplicative rule application. Yeah. Why? Because we want to find out probability of defective 1 and defective 2. Yeah. First cassette and second cassette. Okay. Yeah. Because you see here, what is the probability that both are defective? Defective 1 and defective 2. Yeah. So based on the multiplicative rule, if defective 1 times with defective 2, that means you just need to multiply them. Yeah. Probability of defective 1 times with probability of defective 2. So that would be 4/10. Oops, I didn't draw the probability tree. Oh man. I think this is because you have it in your notes. Yes or not?
Fair enough.
I can show it here also. Wait, so I have to go and look for it. It's here, kan, in this classroom of ours. Classwork.
Don't have.
I think that's the reason why I didn't show it, because I think the probability tree is there. Yeah, this is the one. Oh, it's not. Can? Oh man, then I guess I have to draw it. Since it's not there, so let me draw it now, just to visualize, to help you visualize what it means. I don't want to show the value yet. And basically, we have first D. Don't mind my handwriting. D1 also, but this one is defective. So there are 20 cassettes here. So 16 over 20 and 4 over 20. Hope you can see it, yeah? And then, because we want to take 2 cassettes, so this one would be D1, D2. This would be D2 also, the second take. Yeah, this one it would be D2 also, and D2 with a hat. So notice here, because it's stated in the question with replacement, therefore, my labeling is a bit off lah. I don't want to confuse you guys, because what's stated here is D1 times D2, right? So terbalik lah, I write the bar. It's here. This is the one not defective lah, basically. But we want defective, right? So you see, we have 16 over 20 not defective and 4 over 20 as defective. Yeah, so up here, because it's with replacement, therefore it's still 16 over 20. Here would be 4 over 20. And then 16 over 20. And then 4 over 20. Okay, so if I want to find out both are defective, D1 and D2. Yeah, so that means this is D1 and this is D2. And you can see the value is 4 over 20 and 4 over 20, which you can see here, 4 over 20 times 4 over 20, and that gives me 1 over 25. Is that clear?
Okay.
Okay.
Okay. However, oh, it doesn't ask here, but I just want to give you guys a different scenario. Say if the question state, let me change my pen. Say if the question state here, without. What do you understand if I write here without replacement? That means the second pick, the number would reduce. That means first pick, it's still 16 over 21, 16 over 20, 4 over 20, still the same. But when we go to the second pick, because here you have taken out one non-defective, it will become 15 over 19 here. Remember, the blue is with the blue value also. And here would still remain as 4 over 19. Because here, on this particular branch, only the defective, non-defective is taken. So that's why it reduced 15 here. But in this case, the defective are taken. So here 16 over 19 doesn't change. Remember, it's over 19. But down here, it will become 3 over 19. So if the question is without replacement, the answer would be 4 over 20 times 3 over 19. Is that clear, class? So that's the difference. So you have to be careful if the question is with replacement. That means the value are in red, no changes. As you go to the second selected cassette. But if it's without, notice that the value reducing. Is that clear, class? Hello? Any question?
No.
Oh,
Kelvin? You okay, Kelvin?
Yeah.
Okay, good. Noel, how about you?
yeah. Okay.
Farah, okay?
Yep. Okay.
Okay, that's good. Quite easy concept today. So since we've done that, yeah, example 18 I would want to go through, but we only have about 4 more minutes, and I don't want to, touch on that yet. We'll do this in the next class, or maybe do it tomorrow during our tutorial, see how it is, just to finish up this topic. Yeah. But of course, let's look at the tutorial question now. Yeah, for us to discuss tomorrow. Yeah, so this one is the question. Let's go to the tutorial question. Which tutorial have you done? Tutorial 3 was the last one, right? The other day we discussed. So today would be more on tutorial 4 for tomorrow. For tomorrow discussion, I don't think you can do question number 12 yet. No. I would prefer you to do. Since they are all short questions, let me see this one if you can do number 8 already or not. Given day. This is conditional also. So can you do question 1, all the even numbers? Can you do even numbers only? 2, 4, 6, 8. Tutorial 4. Can or not, Clara?
Okay.
Yeah. Even numbers, tutorial 4. Let me jot it down. If not, I'm very bad at my memory. Yeah. Tutorial 4 for tomorrow. Question 2, question 4, question 6, and question 8 for discussion tomorrow. All right. Is that okay? Yeah. So any question to what we've learned today?
So far, no.
So far, no.
Okay, Farah. Kelvin, all right?
Yeah.
Okay, so I'll see you guys tomorrow, 1 p.m., right?
Yeah.
Okay. Bye, everyone. Have a good day.
Okay, Miss. Thank you.
Thank
Thank you, miss.
you. Thank you. Bye-bye.